So, I of course want to do the whole caveat that my name is Craig Wayson and I am not a statistician. Sort of get that out there right now. But sometimes it's this convergence of groups of people, statisticians, people who work with carbon estimations, and working together. You see we have quite a few people here. We can do some interesting analyses, or at least what I think is interesting. So we have this analysis, sensibilidad de modelos alométricos, with that wonderful acronym of ASMA. So perhaps we'll have to think about changing that later or not. So our objective was to start looking at the behavior of the statistics and the characteristics of alometric models to understand a little bit better how they function, what happens with, and we've seen a lot of presentations this morning that talk about sample size, distributions, choice of models, right? So we actually wanted to do this in sort of a semi-real world experiment. Basically because this whole idea originated from the fact that Mexico has about, I think, 500 allometric equations that they're using in their database, and they have a decision tree to choose them, right? Well, I was talking to Osvaldo one day and I was like, well, how do you choose the ones that you choose for the species if you have them more than one per species or type of species, group of species, or whatever? And so he was telling me about the decision tree, and I was like, well, how do we know what the uncertainty is based on just your decision tree process? And so we decided to go ahead and do something a little bit different that we're just getting going. We have some results to show, so hopefully we'll get some good feedback here. So we'll talk a little bit about what I'm going to call this fake forest that we've created. Talk a little bit about some of the analyses that we're doing, calculation of the proper N, and then look at the sensitivity of these allometrics and show you some results from that, and then look at where we're going to go from there. So, this fake forest. One thing that I guess kind of comes to mind when we talk uncertainty, we often get stuck in the whole idea of, well, what is the variability of our data, what goes on in there, how do we choose our models for that? And I would say that it's not necessarily the model's fault if we have crappy data, right? Sometimes we want to choose the right model for our data, but actually we're trying to look at what is the value of the actual population, right? So sometimes I think we get caught up in all this and we forget that we're trying to estimate uncertainties of something real that's out there, not necessarily the variability of the data that we're seeing. Now, so hopefully we're choosing good data, we're getting good representativeness, etc., so that we can equate those and say that yes, we are representing the populations. But particularly, excuse me, with allometric equations, due to the nature that it's hard to chop down trees, it's a lot of work, a lot of places you can't, since there aren't many trees left in the Andean region, right, in the upper areas. So that's just poor data, and we need to figure out, well, how can we best choose those models even when we have crappy data. So what we decided to do was create a fake forest, because we wanted to understand how these choice of N, distribution of N, model choice actually affected the uncertainty in real terms of actual biomass of our forest or our population, okay? So basically this kind of comes out of some work that I used to do, been doing a little bit, when trying to estimate or generate uncertainty estimates for allometric equations where we have little information. And so you can do what's called a pseudo analysis, where you can create a fake population that has characteristics similar to the population that your model represents, hopefully. And so what I did here is we went ahead and created a fake forest of about 1 million trees, and we tried to make our fake forest as real as possible. So we looked at the data that came out of the Mexican forest inventory, all the trees there, to look at sort of the range of distribution, diameter distributions that were there, and then had the distributions of those diameters, and then to generate sort of understand the variability, because we all know the bigger the tree, the larger the variance is on those biomass numbers. We had a data set that comes out of Canada where they have about 6,000 trees, I think, total, where they've actually chopped them all down, weighed them up, and so we had an idea of what that variability is per class of diameter. And so we created a fake forest that somehow represents that. Obviously, my fake forest, I had to choose a real biomass, so I just generated biomass numbers based on the diameters using a simple equation here. It's a pretty standard one. And for right now, we're only looking at diameters. This is, of course, work in progress. As we go along, we can make it more and more and more and more complicated and more real world, hopefully. So when we were sitting down starting to do this, obviously we're like, well, what are we going to do? What are some of the things that we need to know? And so, as I always say, it's not a napkin, but a whiteboard is almost as good, maybe a little bit better, so we can draw out some of the things that we're trying to look at. So, with our fake forest, we went ahead and calculated what would be the optimal size of trees chopped down and size classes. Now, this is, of course, using Neyman's technique here to generate that based on number of individuals, right, and the distributions. Probably we should go back and actually not use number of individuals and look at the term that we're trying to estimate, which is actually biomass. So we may adjust these numbers. But if you look at this, if we use, because we have a lot of trees down here, I don't know if you can even see this down here in the back, a lot of trees in the lower end of our diameter ranges, this process will of course say we should pick more number of n in that class range. So starting from that starting point, we know that we have n of 104 is probably going to be our optimal choice, which we'll adjust later on. But what we wanted to look at then was, okay, what about the distribution of n? So we have our optimal distribution, one that's sort of an intermediate range, and then one where it's a little more representative in the sense that it concentrates the number of individuals we're using to generate, parameterize our models in these smaller diameter classes, which is pretty common just because smaller trees are easier to chop down, less valuable, and so we often will find distributions where they tend to be concentrated on the lower end of the scales. Then we of course want to look at the models. So we have about 9-10 model choices that we're looking at, pretty standard ones, all only diameter based. These came out of the forums came out of the Jenkins data set, where she was able to go ahead and kind of break most allometric equations into about 9 groups of the same forms. And then from there we look at the root mean squared errors, the R-squares, and then an actual measure of uncertainty, a true uncertainty, right? We know how much our forest weighs because we made it, right? So then we can look at how these models will predict the weight of our forest and actually generate a true uncertainty. Then of course we can shift down the n, do this over and over and over and over again, looking at an n of 10, using the same sort of thing, right? So as you can see, thousands of combinations. We're able to do a few of them, but because of the power of computers, it's really just a matter of programming it, plugging it in, hitting go, and waiting for your results. You gotta love huge tables with small numbers that you can never really read. But this is just sort of an example of how the breakdown is with these. We have our different numbers of n. We have 6 is of course the most optimal distribution. 3 is that intermediate. The 1 after that is the concentrated in the lower diameter classes. And we chose 104, 80, 60, 40, 20, and 10 as our n. Now, for this first run, when we pulled out a random data set that we're going to use to parameterize our models, we only pulled out one set of data, right? Eventually we're going to go ahead and start pulling out data, random points from our population over and over and over and over again. But to make things a little computationally easier to do right now, we went ahead and just chose one set of data from which we then used to check the performance of these models. These are the standard equations that we're using, looking at here. You can get these right out of the Jenkins. A lot of these are pretty common that you'll see in use. A lot of times it gets kind of crazy where they look at these, but a lot of these equations may have this form, but the constants will be dropping out depending on whether or not you're using them in the equation, right? So there's actually 9 equations here, but the permutations on this are, of course, quite large as well. So someday in the future, we can go start working on that as well. All right, so when we first set out to do this, I guess I was thinking that we would have kind of predictable results. But one of the things that we saw is that things were not as predictable as maybe we had thought. If you look here, I need my notes because I can't remember the colors very well. Thank you. So model 4, you can barely even see, is this blue model here. Red model is model 5. Model 2 is in green. And model 6 is this sort of violet kind of color here. So as you can tell, some of the models just really don't do very well, depending on, as you're moving through, your optimal distributions with different ends, intermediates with different ends, and of course concentrating with different ends. Okay. When we were working with these, for right now, we went ahead and did our fits using nonlinear routines, which is sort of the best, but sometimes there are problems with convergence in these models. If you're doing it and you want to set it up and run it and not really think so much about spending time trying to choose initial parameter estimates that lead you to decent convergence, we had some issues with that, so we'll have to go back and fix that. So as you see, sometimes the models generally perform quite well when you have reasonable n, optimal distributions, but not always, right? The black dots in the background are the million trees. So we have the biomass variance is increasing as our diameters go up. We went from about, it was about 7.5 centimeters up to about 83 centimeters diameters were about the range, just because that's what was seen in the Mexican forest inventory. The underlying model of the trees is this. Right, some would fit better than others based on the fact that our fake forest is created from a model, right? We introduce variability on the back side of that. Sorry, I should probably repeat this so that people can hear it. Right, but curiously enough, oftentimes the model we actually used to create our fake forest was not the model that best predicted by the biomass for the populations, just depending on what n we were choosing. So as we went through this look, we'll be able to see this in graphical form as well. As you see that as the n is increasing, standard errors, right? The standard errors are going up with the distribution of n. So as we have the more optimal distribution, or actually our standard errors are increasing, right? Which is something that was like thrown us for a loop there for a second. We were like, well, that shouldn't be it. We're having a more optimal distribution. Why is our standard errors increasing? And then we're like, well, duh, we have larger diameters in our data set, so therefore it's going to go up, right? So nothing too surprising there, except for that little thing that was like sometimes we forget about when we're doing all this kind of work. So let's take a look at these in graphical form. So basically, the root mean squared error performance, as you see, this is diameter classes ranging from smaller, n, lower n to higher n, and then the 1 is the concentrated, the 3 is of course the intermediate, and the 6 is that optimal. And so with low n and having the optimal distributions, our root mean squared error increases, right? And that's pretty much across the board as you see that. And so that's something to keep in mind, because earlier on when the decision tree was being created for choosing which allometric model to use, to select, they chose whatever model had the smallest root mean squared error has got to be better. Well, it's not really true, because you need to take into account the diameter ranges over which it was created. Taking a look at the R square, again, depending on the model, right, there aren't any general patterns that are going on here just yet. But we do note this again, that of course our models the actual values of the estimates of the uncertainty are changing in a way that's intuitive if you stop and think about it, but a little counterintuitive if you're just looking at, well, we want to choose the one that has the, you know, the best R-squares, etc., right? But it's not always the case. But it generally, R-square tends to be a better choice when you're looking at this, if you're not taking a look at the root mean squared error in terms of adjusting it for the diameter classes. And now the part that everybody's waiting for. Depending on the model choice and the n and the distribution of n that you're using to parameterize those models, your actual true uncertainty can really bounce around quite a bit. So the model number 5, as you can tell, can tend to overestimate greatly, but then as you get maybe choosing 60 trees with different distributions, it'll tend to underestimate just by the model form that's there. This is one random sample, one set of data. Obviously, it's to come back, and we should be able to create more sophisticated and general analysis, and that's what we're going to be looking forward to doing. Model number 2, for example, tends to underestimate if you're parameterizing it with smaller numbers of n's. And then as you get out here, if you have more optimal n, it tends to get pretty close to the actual true value. And model number 4 is generally pretty good, except for certain cases, right? So what we were seeing here is that model choice, model form, distribution, and size of n are all important factors. You know, we saw a lot of talks this morning that were kind of talking about each kind of piece, and so this is a way that we hope to kind of throw them all together at once, so we can look for those optimums in terms of n, distribution of n, model choice, right, into the future. So, some sort of conclusions from this. The size of the sample and its distribution does change the model that best adjusts to the data. I mean, this is not anything that is probably earth-shattering science here, but at least now we have ways of quantifying what that means in terms of uncertainty, right? We'll at least be able to look at what that is doing to our uncertainties numbers. Uncertainties in the predictions diminishes when the models were chosen with n size bigger and better distributed, right? Something else. Okay, that makes good sense. It's good to know that we're doing this, right? But one of the things that we want to look at, though, is try and minimize that. Is there some point where we can look at all three of those things that we need to look at that we can minimize, because we can't be running around chopping down trees all the time, right? And so the idea is to try and look for that space in there where we can maximize cost, benefit, and quality of our models. The scale of the data shows that, you know, the root mean squared error is, of course, something that we need to go back and maybe take a look at that decision tree and adjust and say, okay, well, root mean squared error was our top one choice, having the smallest, but maybe that's not really the case, and so now we'll need to go back and adjust that decision tree. The R-square does not follow the same tendencies as uncertainty, right? So choosing a model with the higher R-square does not necessarily lead to an outcome of the lowest uncertainty, right? Because this whole problem. We choose models to fit our data, but if we don't have very good data, or not, suboptimal data, right, then of course it's not going to do us any good when we're trying to actually estimate uncertainties for that true population value. So some things that we're going to try and move on with is, of course, just for first kind of cut at this, transform some of these models into linear so that we can actually run them through, all of them, quickly, because there were problems with convergence, and if you have to sit down and then like choose decent kernel size or starting initializing parameter guesses, etc., and everything, it gets pretty tedious when you're trying to do this for 10 models, hundreds of different distributions, right, sizes of n, etc. And so just to take a look at that, we'll probably convert them over to linears just so we have can eliminate those issues, which of course will generate our uncertainty. And maybe in this process, through the transformation, we can also quantify and start looking at, well, how much does it affect the sort of log transformations on our uncertainty in the end. So we'll create this routine, changing the population size and distribution of the intervals, and of course start pulling over and over and over and over again random samples, just so that we're not choosing out of the same set of trees every time, because these results are of course showing how our original draw from our population was fitting with the models, but now we need to actually go back and just keep drawing every time we do this. Wrong button. Estimation of uncertainties, Niville prediction level, and not, oh, this is something, I'm not a statistician, this is something that, this is, I think, Humberto, I think this is your idea here, to start playing around with some of these things. Once we convert them over to linear models, we can actually start using some other methods to look at the prediction of that biomass and see how well these models are doing. And then, of course, eventually, once we start producing thousands of these results, we'll be actually be able to create sort of surfaces over which we can start looking for that. Is there a sweet spot where we can adjust number of samples, distribution of samples, right, and model choice to somehow look for one that can minimize all those as much as possible. And visually doing that would be easy thing to do. I'm sure we could sit down and do it mathematically once we have all this data, right? But so this, hopefully next time we have this workshop, we'll go ahead and have some true results to take a look at. So with that, thank you very much.
Secretaría de Medio Ambiente y Recursos Naturales.